All right, everyone, welcome to Unit 2, which is on sequences and series, arithmetic and geometric sequences and series to be more specific. Here are our objectives of the lesson today. We're going to identify a sequence as arithmetic, geometric, or neither. We are going to learn about explicit and recursive rules for the general term of an arithmetic and geometric sequence, and we are going to model and solve real-life problems using sequences. So first of all, what is a sequence? Well, a sequence is a list of numbers that has some kind of pattern or rule, right? So you're looking for a pattern in those numbers. Are they in a particular order? What's going on? Or are they just random values? So here it says, what's the next number in the sequence? So if there is a rule or pattern, you should be able to find it. So here we're going to add 3 to get from 0 to 3. Then I'm going to add 5 to get from 3 to 8. Hopefully you're seeing, okay, this is 7, and now you're noticing a pattern. 3 plus 5 plus 7. Now I'm going to add 9. So what do we think the next number is in the sequence? Hopefully you're saying to yourself, it should be 35. Now notice we have some terminology here. It says this is my first term. It's this first term here, and then it goes first term, second term, third term. This is my fourth term, 15, then it's fifth term, sixth term, and we can keep going on and on and on and on, calling, the 77th term. It would be somewhere in there. So we can keep going until we get to the nth term. So if we don't know where that pattern ends, then we can just call it the nth term. If the sequence goes on forever, we call it an infinite sequence. If the sequence actually ends, then we call it finite, right? So if it goes on forever and ever, it's going to go to the nth term, whatever that is, or never stop. If it ends, it could end at a specific term, which could also be called the nth term, or it could be the 17th term or the 22nd term, etc. Okay, we can think of a sequence as a function f from the indices n to the numbers in the sequence a sub n. So n, this is what we're inputting. We're inputting a 1 to get a sub n, our first term, right? So we put in a 1, we get our first term. We put in a 2, we get our second term. We put in a 3, we get our third term. If you input a 4, you would get your fourth term. If you input 105, you would get your 105th term. So here you're inputting, again, the number 1. Your input is which term you want. If you want the 77th term, you're going to input the number 77. The output would be, if you put in the number 77, then you're getting the 77th term, and that's what a sub 77 means. If you look at your example from before, right, with the one just before this, your domain is starting at the number 1, right? We start counting our first term, our second term, our third term. So it's not an interval, right? It's a set of distinguishable numbers, starting with a number 1 and then going potentially infinitely, or if it ends, then we would have some kind of end. And then the range is all of your y values, all of those values you have in the sequence. So in the one before, it started with 0, then it went to 3, then it went to 8, etc. Right? So those would be your y values. All right, let's try an example below. This is just to familiarize yourself with these notations, right? So what does that a sub n mean? So we're going to familiarize ourselves with it and try these questions. So it says find the first 4 terms in each of the following sequences. I'll start demoing this first one, but if you want to pause and do it on your own, that's fine. So the first term would be a sub 1. That means we're plugging in a 1 for n. So we would get 1 squared minus 1. 1 minus 1 is 0. Find a sub 2. We're plugging in a 2 for n. So we get 2 squared minus 1. We get 3. A sub 3. 3 squared minus 1. And a sub 4. 4 squared minus 1. Now that happens to be the sequence we were just studying. So the rule for that sequence that we had to open up our lesson was n squared minus 1. Okay, go ahead and try this second one, letter B, on your own. And then you can compare. So pause now, try it on your own, then compare answers. All right, did you get 3, 1, 3, 1? The first term is 3, the second term is 1, the third term is 3, the fourth term is 1, and that's going to continue that way no matter what number. That's going to be the pattern, 3, 1, 3, 1. So hopefully you got that. Okay, moving on. Now we're specifically going to talk about what arithmetic sequences are. So if you look at these two examples, these are examples of arithmetic sequences. So what do you notice about these? Well, here we're going to add 5 to get to 8. Then we're going to add 5 to get to 13. Then we're going to add 5 to get to 18. So what you might have noticed is we were adding 5. That's what we're doing over and over and over again. So the next number in this pattern would be 28. Let's look at the next one. So it says, what patterns do you notice? Well, here, what am I doing? I'm subtracting 4. I'm subtracting 4 again. I'm subtracting 4 again. If I kept up with that pattern, I would get a -6, and then it would keep going. So hopefully you're saying, okay, well, if I asked you what is an arithmetic sequence, those are two examples of an arithmetic sequence. You might notice that you are adding or subtracting by the same value over and over again. We call that, if it's the same, we call it a constant. And specifically for an arithmetic sequence, we're going to call that constant a common difference, and we're going to use the letter D to identify what the common difference is. So that is what an arithmetic sequence is. It's when you add the same number over and over from one term to the next. So if we start with the first term, in order to get to the next term, the second term, I'm going to add a common difference. So my second term would just be the first term plus one common difference. If I wanted to get to the third term, right, my third term is here, I'm going to add the first term plus how many common differences? Well, hopefully you can see that there are 2. If I wanted to get to the fourth term, right, this is the first term, second term, third term, fourth term, I had to add one more common difference. So I'm taking the first term and adding 3 common differences. Okay, so let's pause and think about that. What do you notice is the relationship between the number of the term, like the fourth term here, and the number of common differences? So if I said, hey, let's find the 7th term. If you look at this pattern right here, hopefully you're saying to yourself, I would just take the first term and then I would add not 7 common differences, but I would only have 6 common differences to add. So how do we know what the common difference is? Well, you should be able to take any 2 consecutive terms and subtract them, and it should be the same number. So that would be the common difference, right? You can take the 22nd term and subtract the 21st term from it, and you should get the common difference of that arithmetic sequence. If I wanted you to find the 105th term using this pattern, hopefully you're saying to yourself, well, it would be the first term plus 104 common differences. So moving on to example 2, it says consider the sequence 3, 8, 13, 18, 23. So remember 3 is the first term. So when you plug in a 1, we're going to get a 3 because that's my first term. When I plug in a 2, I get my second term. Then I get my third term, my fourth term, my fifth term. If I was going to graph that, I would graph 1 and then up 3. Or I would graph 2 and up 8. Or 3 and up 13, right? So this is 3, then this is 8, then this is 13. When I graph 4, I get 18. When I graph 5, I get 23. So what do you notice that you have? Those points are what? What kind of function do you have? Hopefully you're thinking it's a linear function. It looks like a line. Now, should I graph that line and connect those points? No. These are individual, the domain is not all real numbers. The domain for this function is what we call the natural numbers, which are the counting numbers, right? So we have a domain for this, which is the natural numbers or the counting numbers. You start at the number 1. 1, 2, 3, 4, etc. So we're not going to connect that because it's not continuous. Those are isolated numbers in a sequence. So could we write an equation for this? Well, hopefully you can. So what is this part from here to here, right? To get from one point to the other, hopefully you're just saying if it's linear, all I need to do, is, messing with my colors here, write an equation of y equals mx plus b. What is my slope? So my slope is in between here. I'm not connecting those points, by the way. I was just trying to identify your slope there. So what is my slope? I'm going up 5 when I go up 1. I'm going up 5 when I go up 1. So you're adding 5 over and over and over again. That's your slope. So y equals 5x plus b. I can take any one of those points. When y is 3, x is 1. And that allows me to find what my b is. My b is -2. So can I write an equation for this? Yes. I'm going to say that the nth term in this sequence is 5n minus 2, right? It's just this portion of the equation of the line. So let's check. If I plug in a 1, I'm going to get 5 times 1 minus 2. It equals 3. Yep, that works. If I plug in a 5, I'm going to get 5 times 5 minus 2. That's 25 minus 2, which is 23. Yep, that works. So this is the equation of that sequence. So here you go, little wrap up. Arithmetic sequences are linear in nature. We just looked at that, we just saw that. The domain consists of natural counting numbers starting at the number 1. The range consists of whatever terms you get in the sequence. And we have an explicit rule. So in this particular unit, you're going to have a lot of formulas you're going to learn. And we give you a formula sheet so you don't have to memorize any of them, but you do have to know what A sub 1 stands for, and D stands for, and N stands for. We're not going to tell you that when you're taking your quizzes and tests, so you need to make sure you're aware of what that is. So here it says A sub 1 is the first term. You should know that already. D is the common difference. N is the term number, or whatever the subscript is right here, that's N. So here's the formula, and I rewrote what we did on the previous example here because hopefully you're seeing the connection between the formula, that it makes sense to you, right? If we want to get the fourth term, then 4 is the number n. Well, how many common differences did I add to the first term? I added 1 less than whatever this number is, whatever 4 is. So we added 3 common differences. So that's why we have our n minus 1 here. So the formula for the arithmetic sequence to get whatever term would be a sub n equals the first term, a sub 1, plus the common difference times n minus 1. So if we're looking up here at this example from example 2, if I want to find a sub n, I would put in my first term, which is 3, and then I would I would add, the common difference. My common difference is 5, and then I would just put in n minus 1. So I put in my a sub 1, I put in my d, and I'm trying to get the general formula. So the formula, we have to distribute 5n minus 5, so I would get 5n minus 2, which is a sub n. But look at all the work I had to do as compared to just, figuring it out over here based on that linear relationship. So I will probably demonstrate this more in class, but you can use this formula. If you like formulas and you want to plug in, you can use that formula as well. If you're not sure what happened there, then just talk to one of your teachers. Okay, moving on with some examples here. We have the sequence that is example 3, it says consider the sequence 6, 17, 28, 39, 50. Show that the sequence is arithmetic. So when you're going to show that, basically what you need to do is you need to show that it has a common difference. How do you find the common difference? You either subtract a sub 2 minus a sub 1, or a sub 5 minus a sub 4, or a sub 3 minus a sub 2. So any two consecutive terms, one after the other, they need to share the same numerical value, which we call the common difference. So does 17 minus 6 equal 50 minus 39, or does 50 minus 39 equal 28 minus 17? So those should all be the same number. So yes, they are. So a common difference exists. So therefore, if a common difference exists, then you must have an arithmetic sequence. Okay, part B. It says find the explicit rule for the nth term of this sequence. An explicit rule is when you can plug in the number and find that term. So if I wanted to find the 77th term, I should be able to plug in 77 for n to get whatever that numerical value is. So that's what an explicit rule is, and we'll create one now so we can see more specifically what I'm talking about. So we just said the common difference was 11. We're adding 11 over and over again. I'm going to find the explicit rule by using the y equals mx plus b that I was talking about earlier. Right? If we're adding 11 over and over and over again, then that is my slope. So I have 11 repeatedly, so it's 11 times n times. And then I have to add some unknown value, right? Well, you can do the unknown value in your head, or you can choose one of these terms. So I usually just go with the first term, right? So a sub 1 equals 6. So when n is 1, right, I'm substituting in 1 for n. When n is 1, I'm going to add some value to it to get the number 6, right? So I need to get my first term by plugging in a 1 for n. So when I plug in a 1, I'm going to get a 6 value. Well, 11 times 1 is 11, so 6 equals 11 plus question mark. So what am I going to add to 11? What am I going to add to 11 to get to 6? Well, hopefully you're saying that should be -5. So my explicit rule is 11n minus 5. Now I would go ahead and check that. So I would take maybe the fifth term and just check it. A sub 5, I get 11 times 5 minus 5. It's 55 minus 5, which is 50. So yes, that explicit rule worked. When I plugged in the number 5, I got the fifth term. And yes, that is the fifth term in the original sequence. So that pretty much verifies that my explicit rule is correct. It says, is 325 a member of this sequence? If so, which term is it? So I need to set 325 equal to 11n minus 5, and then I can determine whether or not it is part of the sequence. So I'm going to add 5 to both sides, right? And I get 11n equals 330. Divide by 11, so hopefully you're seeing to yourself that yes, it equals 30. It's not a decimal, so it works. All right, example 4. I'm going to show you a different way of doing example 4 than what is in the notes. So if you want to go look at the notes for a different way because you didn't really understand this one, that's fine. But I'm going to show you a system of equations just so you see something different. So here's the formula that we know is what we use for arithmetic sequences. A stands for arithmetic. So to get the nth term, you would take the first term and add to it n minus 1 common differences. So n minus 1 times d. It says we have the fourth term of an arithmetic sequence, and we know that that value is 20. And we know that the 13th term of the sequence is 74. We need to find the first term, so we need to find a sub 1, and we need to find the common difference, which is d. So we don't know either of those things. What we do know is that if we have a fourth term, we can get the fourth term in terms of a sub 1 and d, right? If we take the fourth term, we get to take a sub 1 and add 3 common differences to it according to this formula up here. So now I can just substitute in the number 20. 20 equals the first term plus 3 common differences. For the 13th term, we know we can take the first term and add 12 common differences. Again, because of this formula, we have 1 less common difference than the number of term. Well, the 13th term is 74, so I'm going to get a sub 1 plus 12d equals 74. Now we have a system of equations. We have 2 variables. We need to eliminate one of them. Because both of these have an a sub 1 isolated by itself, I'm going to isolate my a sub 1, so it's going to be 20 minus 3d. I'm going to isolate my a sub 1, that's going to be 74 minus 12d. And I'm just going to set those equal to each other, right? Because they both equal a sub 1. So I'm going to find my common difference first. I'm going to add 12 to get my 9D. I'm going to subtract 20 to get 54. Divide each side by 9, and I discover that my common difference is 6. Now I'm going to use this number, and I'm just going to plug it in. If a sub 4 equals a sub 1 plus 3D, well, 20 equals a sub 1 plus 3 times the common difference, which is 6. So a sub 1 must equal 2. So there is example 4. And finally, for example 5, for the arithmetic part, that is, it's not finally for the lesson. This lesson's taking a long time. But for example 5. So example 5, we say we have consecutive terms of an arithmetic sequence, and here they are. It's 5, k, and k squared minus 8. So 5 is the first term, k is the second term, and k squared minus 8 is the third term. Or they could be the 4th, 5th, 6th terms, or the 8th, 9th, 10th terms, but they're consecutive terms. We need to find the value of k. Well, if it's an arithmetic sequence, hopefully you're saying to yourself, they must have a common difference. So if I take the second term and subtract the first term, it should equal the third term minus the second term. So if I take k and subtract 5, right, k is the second term, and I'm going to subtract 5 from it, it should equal the third term, which is k squared minus 8, and subtract the second term, which is k. Well, you should be recognizing, I hope, we have a hint here that it's value parentheses, so possible values, and you see a quadratic here. We just did a big unit on quadratics. So if we solve or set this equal to 0, right, then we have 0 equals k squared. We move the k over by subtracting k, so we get negative 2k. We add the 5 to get negative 3, and then we're going to factor. So minus 3 plus 1, that multiplies to give me negative 3, adds to give me negative 2. So k is going to be negative 1 or 3. So I have two answers. You could plug them in, make sure it works. So 5, negative 1, negative 7 if I plug in my negative 1. Or I could get 5, plug in my 3, and then I could get 5, 3, and 1. So those are my two sequences. It doesn't ask for that, but you could just double check. Does it work? Minus 6, yes. Common difference, minus 2, yes, common difference. So these are the correct values. How do we then write an explicit rule for the general term? Remember your explicit rule, they just want to be able to plug in a 1 or a 2 or a 3 to get that specific term. So we have two different sequences. I just did this work above. So we have the 5, 3, 1 sequence, and we have the 5, negative 1, negative 7 sequence. So I'll erase this, sorry. So if I have 5, negative 1, negative 7, we just saw that the common difference was negative 6. So a sub n equals negative 6, n plus some unknown number. If I plug in a 1, I want to get to the number 5, right? So I want to get 5 when I plug in the number 1. So what am I going to add to negative 6 to finally get 5? Well, looks like I need to add 11. So I'm going to get a sub n equals negative 6n plus 11. That's one option. And then I have another one where I go minus 2, minus 2. I go a sub n equals negative 2n plus, well, if I plug in a 1, I should get a 5. So what am I going to add to get to a positive 5? Hopefully you're saying I need to add a positive 7. So there are my two equations. If you don't like this, I haven't really showed you, but you could use the formula. If you don't like it, the linear method, right? You're going to say a sub 1 equals a sub n, a sub n equals a sub 1 plus n minus 1 times the common difference. So I'm trying to find a sub n. I have my first term, which is 5. I'm going to plug in my common difference, which is negative 2. So I get 5 plus negative 2 times n, which is negative 2n, negative 2 times negative 1, which is plus 2, and again, I get the same thing as just doing it algebraically or linearly with the slope. All right, now we are on to geometric sequences. So what is a geometric sequence? Well, how are we getting from 3 to 6? How are we getting from 6 to 12? How are we getting from 12 to 24? Hopefully you're saying to yourself, I'm multiplying by 2, so the next number in that sequence would be 48. How are we getting from 5/2 to -5/4? How are we getting from 5/4 to +5/8? Well, hopefully you're saying to yourself that we are multiplying by -1/2. So I would get 5/32. So for a geometric sequence, we have something that we multiply by the same number over and over again, and we call that a common ratio, and we use the letter R to represent it. So if you have your first term, a sub 1, you get your second term by multiplying it by 1 common ratio. To get your third term, you multiply by 2 common ratios, the first term times 2 common ratios. To get the third term, you multiply by 3 common ratios, the fourth term, you multiply by 3 common ratios. So to get the nth term, you're going to multiply by n minus 1 common ratios to the first term. How do you calculate the common ratio? You can take any 2 consecutive terms and divide the larger one, or not the largest number, but the bigger term, the third term divided by the second term, right? Or the second term divided by the first term, or the fourth term divided by the third term. So, and the common ratio, of course, can never be 0, or you wouldn't have any numbers other than 0 in your sequence. Because this is taking so long, this particular lesson, I'm going to skip this example 6. You can do it on your own, right? You can put in your numbers, or I'll do it really quickly. But if you're multiplying by the same value over and over again, what kind of function do you have? Hopefully you are saying to yourself that you would have an exponential function, right? So this is going to be exponential. And how do we get that? Well, exponential graphs are some value times r to some power, right? So you can work that out, but we'll talk more about that as we go through the examples. So I want to get through some examples in this video because it's taking a long time. So here's the formula for a geometric sequence. Geometric sequences, we just said, are exponential in nature. Their domain is all the natural numbers, which are the counting numbers. You plug in a 1, you get the first term, plug in a 2, you get the second term, plug in an n, you get the nth term. A sub 1 stands for the first term of the sequence, R stands for common ratio, N stands for the nth term. So we're still using the letter A, so sorry, A does not stand for arithmetic. It's arithmetic or geometric, so A sub n is just the nth term, A sub 1 is the first term, and R to the power of n minus 1. That's your combo. Find the 11th term in this example here. So it says find the 11th term of the sequence 1, -1/2, positive 1/4, -1/8. Well, whenever your signs are alternating, that means you are multiplying or dividing by a negative number. Instead of doing divided by -2, we always just usually show multiplication and just put a fraction. So you're multiplying over and over again by -1/2. So my common ratio is -1/2. If I'm trying to find the 11th term of the sequence, right, I'm going to use that formula, a sub n equals a sub 1 times r to the n minus 1 power. I'm going to find a sub 11, so I'm going to take my first term, which is 1, my common ratio, which is -1/2. Make sure you parenthesize this, and then you're taking that to the 11 minus 1 power, or to the 10th power. Well, the 1 really isn't doing much. 11 minus 1 is 10. If you're taking a negative number to an even power, then it's going to end up being positive. So that's 1 to the 10th power divided by 2 to the 10th power. Well, 1 to the 10th power is 1, and 2 to the 10th power you can count on your fingers, right? You go 2, then 4, then 8, then 16, then 32, 64, 128, 256, 512, and then finally 10th power, 1024. So your answer is 1 over 1024. I did not need a calculator to do that. My 2's are pretty easy. I'm doing them exponentially. Looking at number 8, It says the second term of a geometric sequence is 6, and the fifth term is 81/4. Find a sub 8. So the second term is 6, and the fifth term is 81/4. I would encourage you to pause and try to set up a system of equations again and see if you can figure out. Think of that arithmetic system that we did. We're going to use this equation right here. So try it and see how you do. So pause and try it on your own. Okay, did you get r to be 3/2? And then when you plug that in, did you get a sub 1 to be 4? And then finally, when you used a sub 1 and r, did you get a sub 8 to be 2,187 divided by 32? So you can leave your calculator in exact form when you're calculating this. And yes, I said calculator. I would use your calculator for this one. Or if you got a decimal, you can just check your decimal and see if it works and if it's the same as my fraction here. But here's my system of equations, right? A sub 2 equals the first term times r, which is 6. So I solved for a sub 1 to get 6 divided by r. Solved for a sub 1 here to get 81/4 divided by r to the 4th. Then I set those equal to each other, so that came down here. 6/r equals 81/4 divided by r to the 4th. And then I isolated r cubed by cross multiplying here and dividing it out to get r cubed equal to 27/8. Take the cube root of both sides to get 3/2, and then the rest I have there. So there might be an easier way in the notes if you want to check that out. I think it's probably a little bit easier in the notes. Check that out, but I did want to show you a system of equations. If you understand the system of equations, that might be helpful for other questions in the long run. All right, finally, we have the difference between an explicit rule and a recursive rule. So what we've been studying so far, these formula that you have, the arithmetic sequence formula, and then the geometric sequence formula, those have been explicit. When you plug in the number 1, you get the first term. When you plug in the number 2, you get the second term. When you plug in the number 77, you get the 77th term. That is an explicit formula. If you have a recursive formula or a recursive rule, that is not the case. Instead, we give you a really simple rule and we give you a starting point, right? So here are the rules for a recursive formula. We always give 2 pieces of information. We give you a starting term, which is typically a sub 1. Where do you begin your sequence? And then we give you a relationship between the 2 successive terms, right? So if we look at this example up here, if a sub 1 is 25, then a sub 2 is what? Well, I have to plug in 1 for n, so that's a sub 1 minus 5, right? So a sub 2 is when we plug in 1 for n, and then we would get 25 minus 5, so a sub 2 is equal to 20. We get a sub 3 by plugging in a sub 2, right? We have to plug in a 2 for n, a 2 for n, so we would get 20 minus 5, so a sub 3 would equal 15. We can make an explicit formula with this recursive formula, but we did not give the formula explicitly, we gave it in recursive notation, but it does form an arithmetic sequence, and that arithmetic sequence you could write an explicit formula for. So let's see that. We're going to do that in this next example. Let's go ahead and try it. So this next example, it says, consider the sequence -2, 1, 4, 7. Write an explicit rule. It doesn't tell us that it's arithmetic, but I can see that I'm going to add 3 over and over again. So I'm going to immediately jump to my rule, which is a sub n equals 3n. That's my slope, right? Maybe you do a little side note. -2 equals 3n plus what number? When I plug in a 1 for n, how do I get -2, right? This is my first term. So when I plug in a 1 for n, I need to get -2. So my question mark equals, well, I subtract 3 from both sides. So I would get a -5. So my explicit rule is a sub n equals 3n minus 5. I'm going to pause. I'm going to check it. Let's check a sub 4. 3 times 4 minus 5. A sub 4 equals 7. Yep, that's right. So I know this, in fact, is the explicit rule. Now, how do I write a recursive rule? Well, there are two pieces of information we need. Number one, we need to have some kind of starting point, and usually that's your first term in your sequence. So a sub 1 is -2. I have to give you that information. If I don't, I have no idea what number we're starting this sequence with. What's the next number going to be, where it begins, where it ends. So we have to start with the beginning. So now I'm going to say the next term, right? So if I want to get the second term, I need to have a subscript here of a sub n plus 1, because when I plug in the 1, whatever term I give here, if I plug in the 1, I'm going to get a sub 2. So what am I doing to the first term in order to get to my second term? I'm just adding 3, right? So if I'm adding 3, then that is my recursive relationship. I'm done. So let's check it. If I want to get my second term, I plug in my first term and add 3. So I plug in my first term, add 3, I get a 1, check. That's what I have up here. I have a 1. If I want to get my third term, I plug in a 2, right? So I plug in a 2 here. So I get a sub 2 plus 3. So my third term is my second term, which is 1, and then I add 3. So yes, my third term is in fact 4. So my recursive rule is right here. We have to first identify the starting point, which is a sub 1, the first term, which is -2, and then I have to say what the relationship is between each successive term. So what am I doing over and over? I'm adding 3. But notice these subscripts are really important. If you don't have these subscripts correct, then you're going to get points deducted from your assessment. So if I want to get to the next term, I need to take the term before it, n, and add 1 to it. So if I want to have the first term, I need to get to the second term, I add 1, and then I use that first term, or the nth term, in order to find the next term. All right, and then the last one's geometric. Try it. So this last example is geometric. So find the explicit rule. Right? How do you find the explicit rule? Hopefully you're saying to yourself, my explicit rule for geometric. You look at the formula. Maybe you don't know it so well yet. You go up, you look at the formula. For your explicit rule, you need to substitute in for a sub 1, and you need to substitute in for r. So my explicit rule is a sub 1, which is 2. My common ratio. What am I multiplying by over and over and over again? Hopefully you see that it's -1/5. And now the formula says I take that to the n minus 1 power. So this is my explicit rule. If I want to find the 7th term, I would plug in a 7 for n. A recursive rule needs two pieces of information. Number one, I need to have a starting point. My starting point is 2, so I have to list a sub 1 equals 2. And then I have to list my a sub n plus 1 equals, I have to take the first term. What am I doing over and over and over again? I am multiplying by -1/5. So I'm taking the first term, I'm multiplying it by -1/5, and that is how I would get the next term in the sequence. Letter C, which rule would you use to find a sub n and y? Well, if I was going to find like the 100th term, would you want to use the recursive rule? Well, if you want to find the 100th term, you have to have the 99th term. And if you want to find the 99th term, you have to find the 98th term. So the recursive rule is not ideal to use. So you should be wanting to use the explicit rule to find a sub n. Right? So even if you had to find a sub 10, you could either just plug in 10, or you could find the 9th term, the 8th term, the 7th term, the 6th term. So explicit rule is going to be easier because you can just plug in the number. All right, that's it. Really long lesson. Hope you understood it. If not, talk to your teacher. Bye.